Hey Adventers, welcome back to our Advent of Code 2024 series. Today we are at day 20 and I am presenting you from a 20-sided polygon which is called an icosagon. And yesterday was really fun. On day 19 we helped a bunch of folks at an onsen to rearrange their towels in multiple designs, and it was a beautiful combination of recursion and memoization to optimize and solve the problem to get the solution. And if you're new here, I'm Jatin Kumar Malik. I'm a principal engineer who absolutely loves solving these problems. And last year I did a Medium blog post series, and this year I'm doing YouTube. So if you haven't check out our last day 1 to day 19 discussions here in this playlist. And with that, let's get started. So day 20 problem is today called race condition. Let's read it. The historians are quite pixelated again. This time, a massive black building looms over you, and you're right outside the CPU. And this is a reference to days 24, 2017. And yeah, we are stuck with historians in a computer. While the historians get to work, a nearby program sees that you're idle and challenges you to a race. Interesting. Apparently, you have arrived just in time for the frequently held race condition festival. Oh, so on a side note, this clearly is a reference to a race condition. And if you don't know, I can quickly explain that. So in computer science, whenever you have a resource, let's say there is this database, and let's say you have two processes. So there is a process P1 and then there is a process P2 who wants to do the exact same thing. So let's say this process here wants to update a name field to, let's say, JK, and then there is this P2 that also wants to update the name field to, let's say, John. And if they both originated at same time, let's say t comma 0, this condition is called a race condition, where there are two different threads that are competing for the same resource to do that. And it says that the race takes place on a particularly long and twisting code path. The programs compete to see who can finish in the fewest picoseconds. So another side note, so a picosecond, if I'm not wrong, is 10 raised to the power minus 12 seconds, which is a 1 trillionth of a second, which is like a very, very, very quick time. And the winner even gets their own mutex. Mutex. So I think I'm just explaining some computer science concepts here. I think there is a link to Wikipedia. Yeah. So mutex is nothing but a lock in computer science, and these locks are present everywhere. It is present in your OS, it is present in your database. Like anytime you access a resource, remember I explained the race condition where there are two processes competing for a single resource. To solve this, what we do is we follow a process where in any race condition, you try to serialize the competing processes, which means you try to organize them one by one, and then you try to assign them locks. So in this case, where if we have two processes trying to modify a database and a single field, we will serialize them and say, like, if there is a queue, we will serialize them as P1 and P2. And while P1 is working on this name field, we will put a lock on it, or we will say that process 1 has acquired mutex, so that while it is updating the field, no other PX process can come and modify that. And it is a very popular pattern, as I said, is in your operating system, databases, and multiple other areas that it's used. So definitely check it out. It will probably make for a good reading. But let's read on the problem. So it says that they hand you a map of the racetrack. That is your puzzle input. So let me copy this to our whiteboard so that we can inspect it better. And let's see what the legends and the symbols denote. So it says that the map consists of a track, which is mentioned by a period. So our period here denotes a path of a track. And oh god, it looks like we have another 2D puzzle. So yesterday was fun because we were doing string manipulation. But prior to that, I think it has been just back-to-back 2D grid puzzles. And today also seems like another one. Anyways, and it includes a start and an end position that is denoted by S and E, which is here. And then there is our hash or pound sign, which denotes a wall. Okay. So it says that when a program runs through the racetrack, it starts from the start position and then it is allowed to move up, down, left, or right. So like we have a program that has 4 directions, so it can go up, down, left, right when moving in the grid. And each move takes 1 picosecond. So basically, whenever you move, it takes you 1 picosecond, which is, as I mentioned, very fast and is 10 raised to the power minus 12 seconds. Okay. The goal is to reach the end position as quickly as possible. In this example racetrack, the fastest time is 84 picoseconds. So if we look at this puzzle here, let's see the fastest time. So we are starting from S and we are moving here. It seems like there is only one path. Yep. Yeah, so I don't see any other path. Let's read that. So, because there is only a single path from start to end, and the programs all go at same speed where we are going at 1 picosecond per tile. So let me fix this. Yeah. The races used to be pretty boring. Of course, I can imagine that if everyone is taking same time, it will end in a deadlock or a race condition. Hence the name of the problem. To make things more interesting, they introduced a new rule to the races that programs are allowed to cheat. Very interesting. So we have some kind of a cheating mechanism. What does it mean? So it says that the rules for cheating are very strict. Exactly once during a race, a program may disable collision for up to 2 picoseconds. So once for a race, we can collision. So collision, I think I'm assuming, is a wall. So we can remove a wall for 2 picoseconds. And what does that mean? This allows the program to pass through walls as if they were regular track. At the end of the cheat, the program must be back on normal track again. Otherwise, it will receive a segmentation fault and will get disqualified. And I think this is another link to seg fault. So seg fault is very popular concept in programming if you have worked especially on C or Java or C++, where it means an access violation whenever you try to access a memory space that either you're not allowed to or either that does not exist. And if you have ever used Java, like null pointer exception, NPE in short, is one of the most popular examples of segmentation fault. But that makes sense. Like, so your program needs to be back on track, essentially, I think. So a program could complete the course in 72 picoseconds, saving 12 picoseconds by cheating for the 2 moves marked 1 and 2. And let's see that. So our original path was just following this one. So if I had to draw that, and like you saw that the original path was fairly long, that was going like in this manner here. And it says that if you can save 12 picoseconds by cheating on the move marked as 1, 2. So in this example, it's saying that if basically we remove this path, this block, instead of going through like this, from here, our program can basically just go like this, which means that you will save 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And obviously, it's not 13 because you add up extra here, right? It says like whenever you cheat, it takes 2 picoseconds, which is 1 here and 2 here. So you end up saving basically 12 picoseconds here. So that I understood. And similarly, I think we are given another case where a program could complete the course in 64 picoseconds by saving 20 picoseconds by cheating on the moves marked as 1, 2. So which is given here, which means that if I had to revert this, it seems like if you start going like this and you come here and it's saying that if you remove this one, you can just directly jump here and then you don't have to go here at all. And this will save 20 picoseconds. And of course, we can see in this example that probably the fastest way would be here if I'm going like this And if I remove this one, I can directly reach the end, which will probably be the best path. But let's not get ahead of ourselves and see other examples. So it again says that if you remove this one, which is this block, you can save 38 picoseconds. And then there is, of course, this one that I was mentioning, and it directly goes to the end and it saves 64 picoseconds. Fairly okay, understood. And each cheat has a distinct start position, the position where the cheat is activated, and just before the first move that is allowed to go through the walls, and the end position. Cheats are uniquely identified by their start position and end position. So that's why we are denoting it by 1 and 2, where it means that because it takes 2 picoseconds, your 1 should be the one which goes around the wall, and 2 should be the one that goes back on the track. And if we can see all of these examples here, comparing it to the previous example, like 1 position is wherever there used to be a wall, and 2 position is just going back to the track that was there. So essentially, in a way, like if I have to explain this in a simple words, like whenever you are doing this cheating, what you are essentially allowed is you can think of it as in multiple ways. You're allowed to either create a bridge, or either you are allowed to demolish the wall, or you are allowed to assume just one of the hash positions as a dot, whatever makes you understand the problem in a more simple way. So let's see, what do we have to find then? Each cheat has a distinct start position and end position, and cheats are uniquely identified by their start and end position. So we have to keep a track of this. So this is how a cheat is defined, like the 1, 2. And in this example, the total number of cheats grouped by the amount of time they save are as follows. So they did an analysis, and they say that like there are 14 cheats that save 2 picoseconds, 14 that save 4, and so on. And then we have one cheat that saves 64 picoseconds, which is this one, where we just don't have to iterate through all of the grid, and we just can directly get to our end position by jumping over this wall here. So you aren't sure what are the conditions of the racetrack will be like. So to give yourself as many options as possible, you will need a list of the best cheats. How many cheats would save you at least 100 picoseconds? Okay, fascinating. This is a very interesting problem. So now what we have to find is, we have to find the answer. So the answer of the puzzle here would be for us sum of all possible cheats that will at least save 100 picoseconds, which means like that will save you more than 100 picoseconds. We have to find that. So basically we have to find all the cheating paths, but we have to only keep the ones that are saving us over 100 picoseconds. And then you have to calculate a sum of that. And to begin, we are given our puzzle input here, which is a giant maze. And if we had to locate our start and end position, so we can see our start position is here and our end position is up here. So yeah, so I think it seems like the problem is fairly clear to me, but I think now is a good time for you to pause and think, and probably a good time to do a dry run yourself by maybe drawing this and trying to iterate and see what are other cheats that you can find from this list that is given here. And once you're back, I will discuss some of the hints and strategies that are going in my mind to approach this problem, to find like how many cheats can we find to save at least 100 picoseconds. So once you're back, we'll discuss that. So see you in a bit. Okay, so here are some hints to get you started. Let me grab my orange marker. Hints. So I think one of the first things you need to think about is that how would you solve it if there was no cheating allowed for that case, which is basically finding a path from start to end and a shortest path. And it seems like from an example that there is exactly one path, but you first need to find that. And why is that? So that will give you a baseline. And you need this baseline to compare like how many picoseconds you can save. And this. And can you think of what algorithms come to your mind to find something like this? We have been doing this from last couple of days. So one of the first things that comes to my mind is a BFS, a breadth first search, where we start with the points start and we go in all four directions where it is eligible to iterate over a path, and then we keep going till we find the end. And by doing this, you will have like, depending upon how you save that path, you will have a path. And by counting the number of tiles, you will have like how many x picoseconds does it take to traverse from start to end. And the second most important thing here is, if I scroll this up, that how can you represent the state of the race, right? So if you think of this like whatever you call it, a grid or a race, you need to think of a way to store this position so that you can efficiently do the calculations. It doesn't matter if you have cheated or not. So I think a 2D array or a list of lists comes to my mind, which will help us store the current position of us, keep a track of things, and give a nice way to us for us to locate the path and the current location of our program, which is running the race. And I think once you do that, you need to write some helper functions to allow you to track two things. So we have to track time taken, like till a given instant, and like track a position of our program. And now the third one is the important aspect where we have to see like the cheat part. Remember, which can only go for 2 picoseconds. And in 2 picoseconds also, in the first picosecond, you are allowed to go through the wall, and then you have to be back at the path. And this should give you some idea, right? Because this essentially means that you run the initial BFS to find the optimal path. But then at every point that is eligible for cheating, you will run multiple BFS to see if it helps you save at least 100 picoseconds. So greater than equal to 100 picoseconds. That is what we have to find, like how many cheats are possible. So in this example, what I can think of right now is, which is fairly early, is if we see the original example that was given to us. So if I copy this here, and if you see this, I think heuristics are very important. Like whenever you're solving a problem, just studying your input puzzle, I think that is one of the best ways to look at it. And if you look at your start position, what are the possible positions of cheat? So remember, when I say cheat, like a cheat is happening at 2 positions, 1, 2, where our first position is the obstacle, and second position, we have to be back on the path, no matter what. So by looking at this and looking here, you can already see that obviously this, you cannot go this path because this goes out of bound. You can definitely go here, but this already is a path, and then this should be a part of our baseline path that we created. So we don't need to go here. When you go right, you will need to check if you find a wall, you need to see what is after the wall. So you need to check for your 2 neighbors whenever you are looking to cheat. And if you think the second neighbor is back on a track, that is a valid cheat. So you can definitely go right here. But can you go down? Like, well, when you go down, you will not emerge back on a path because that is an obstacle. So you cannot go down here. And now essentially this gives you a way to optimize that. Instead of checking for each and every tile, all you need to do is you need to traverse on your baseline once you find it. And at each position as you move, so let's say in the next position you are here, you need to find out like what are possible cheats from here. And not all positions will have cheats. So as you can see, like on this position, there are no cheats. On this position, you cannot cheat because you cannot go up. You cannot go left because that is a part of your path. You cannot go down because there is a hash and a wall. And on the right, there is a path. And this will allow you to find all the possible paths where you can cheat. So you can definitely cheat here where you can jump here. You can definitely cheat here where you can jump. And here you again cannot cheat because you won't want to go back and you don't want to do this. Similarly here, there is nothing to cheat, can't go up, can't do anything. So this won't be applicable. But here you can again cheat on the right side because if you see, you can jump over the fence. Here also you can go right. And here again, there is nothing for you to do. So similarly, I think one of the interesting ways to iterate here is to find all the possible eligible cheat positions, cheat from there, and then do a BFS again. But that seems like a bit too brute forcey, right? Because if you look at our input puzzle, it's huge. And if you do a BFS again and again, that is not going to help you. So I think another optimization is, can you think of an algorithm that we did in last few days where we were doing a pathfinding, but we were able to assign a score or a weight. Because remember, essentially what we want to do is we want to find all the paths, cheats, all the cheats where we will at least save 100 picoseconds. So does something come to your mind? Well, right. So I think Dijkstra is one of the prime candidates here, because in Dijkstra algorithm, as you go through the path, you tend to keep a score and a bookkeeping of how much score it is till this path right here before you are going to reach the end. Which means that in the original example, if it was taking, how much was it? 84? Yeah. So in the original example, if your baseline takes 84 picoseconds, it means that if I write this again, and if I draw this path, you can almost give, if I take orange color, you can almost start to give a score to each position. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. As you reach end, it will be 84 score, which means that you now on a baseline know that what is the score of reaching at this position. And that means that whenever you do a cheat and you go from here to here, you have two type of scores where you will have your baseline score, which is X, and you will have your cheating score, which is Y. And then to find the number of tiles, number of seconds that you're saving by cheating, all you need to do is you need to find X minus Y. And that will be your delta for how much time you can save to cheat. And I think with this, I think I've basically given the answer here, but with this, I'm going to go ahead and write some code. And I suggest you to pause the video right here and give it a shot and see what you come up with. And if you get an answer, we'll be back in a few minutes and we'll try to see and put it here and see if our answer works or not. So all the best. Hey, welcome back. And as you can see, we have found the right answer for the part 1. It took me 20 minutes to write the code because it just got a little bit too complicated. So I made sure to write it in a very clean manner so that it's easy for me to understand and extend it for the part 2 if you need to. Sometimes investing a lot of time in writing good code initially is good because then your code is scalable and then it's much easier to optimize. And I followed exactly what I discussed here. One of the important optimizations and breakthrough was the thing that I talked about, that you just need to do the BFS once initially to find the path and to find the score. And you need to find a way to score two type of distance. So I maintained two map where there was one that's called distance from start. And then I maintained another dictionary that was distance from end. You can combine both of them if you want. And the idea was that for each coordinate and each path on the tile, I just calculated like how far have we come from the start and how far we have to go till the end. And what that helped me with, that when I was simulating for the cheats in my second iteration that I explained, and I was looking at the valid neighbors, as soon as I executed a cheat, which means I skipped a wall somewhere and I landed on the path, to calculate if this is saving us 100 picoseconds or not was as simple as just taking the, let's say this was like cheat distance from start, and then just doing a subtraction from my distance to end, and doing a subtraction from my distance to start, and that would tell me like how much time I can save till we have to reach the end. And that was a really powerful optimization that helped me solve this problem. And I hope you were also able to solve this problem. And if you had an interesting way of solving this that you would like me to know, just put that in comments and I would love to read that. But with that, let's move on to part 2. And let's read that. I'll just make some space, pick up, let's say the green color, and let's read that. So it says that the program seems perplexed by your list of cheats. Apparently, the 2 picosecond cheating rule was deprecated several milliseconds ago, because we are in a computer, right? Everything is just happening really fast. And the latest version of cheating rules permit single cheat that instead last at most 2 picoseconds. So this is interesting. So in part 1, the length of our cheat was 2 picoseconds. But I think in the part 2, there is like a new rule that allows a cheat to be as big as 20 picoseconds. And remember in the first part when we said it's 2 picoseconds, it meant that we can cross a wall and then get on a path by the end. And this is not complete. It is at most 20 picoseconds, which means that your new cheat can be greater than equal to 20 picoseconds. And I'm sure there is the same rule that at the end of the cheat, you have to get on back to the path. But let's read that. Now, in addition to all the cheats that were possible in just 2 picoseconds, many more cheats are possible, of course, because you can just now run through the walls and get to your end. And this 6 picosecond cheat saves 76 picoseconds. And if you see, so if I get my original input that was given to us, and I put it here, you can see that we are given a cheat here in this example that is basically just rummaging through this here. And then it is going like this, where it is going through 1, 2, 3, 4, 5, 6. So like 5 tiles, and it is taking 1 extra time when it is hopping here. So it's taking 6 picoseconds to get to this hop. And then it is reaching to the end position from here. And it says that because this cheat has the same start and end position as the one above, it is the same cheat, even if though the path taken during the cheat is different. Oh, so we are given another path. And if I change the color for there, we are given this path right here, which is again landing here. And this is also taking 6 picoseconds. And this one was also taking 6 picoseconds. So it is saying that it is considered same because it has the same start and end position. So they both are landing here. So, and this is both starting here. So this is very important that a cheat is considered unique if your cheat start position and your cheat end position are same. So no matter how you go. So in this case, there can be one more cheat here, which is starting from here and then probably end here. And then there can be one more cheat where it is starting like this and it is ending like this. They all take same number of spaces, but we will consider that as a unique cheat. So that will require some interesting bookkeeping for us. But it's good for us because it helps us reduce our sample space, because if you were to store this, that will help you. But we'll talk more about that during the hints. And it says that cheats don't need to use all 20 picoseconds. So it's less than equal to 20 picoseconds. And cheats can last any amount of time up to and including 20 picoseconds, but can still only end when the program is on normal track. So yeah, so whenever you do like a cheat, it can be up to 19 positions here, but the last position, the nth position for the cheat, should always get back to the path. That's what we are doing here. If you see in this example also, when we start the cheat, we get back on the path. And any cheat time not used is lost and it cannot be saved for another cheat later. So you can still do only one cheat, which basically means that when you are cheating, it can be like one continuous cheat position. So when you go through the walls. So you will still need a list of best cheats, but now there are even more to choose between. Here are the quantities of cheats in this example that can save 50 picoseconds or more. So now you can see we have exponentially more paths that will save us more than 50 picoseconds, because if I have to draw my original path using some completely different color, my original path was like with this violet color. If you see, it was taking 84 picoseconds, if I'm not wrong. And now anything that will save over 50 picoseconds is the path that we have to find. And we can see like there are a lot of more examples that are possible, because even in this case, if I take yet another color, maybe a teal color, there is a position where I can actually go like this, and back to this position, and then still go and still save like all of that path that was missed by allowing me to save still more than 50 picoseconds. And we are given some of the examples that there are 32 cheats and 31, 29, and then there are 3 cheats that can save 76 picoseconds. So now find the best cheats using the updated cheating rules and how many cheats would save you at least 100 picoseconds. So our question requirement is still the same. We have to find like sum of all cheats that will save at least 100 picoseconds for us. But the cheat requirement has changed considerably, where our cheat can now be as long as 20 picoseconds. And with that, I think it's a good time. And this is a complex problem, right? Like I can already imagine the search space is exploding with all the possible options. But yeah, so this is a good time for you to pause here, think, and look at the example that is given us and analyze the question to think about how will you build the part 2 on top of part 1. Essentially, the logic is still the same because there the cheat was only lasting for 2 picoseconds, but now it can last up to as long as 20 picoseconds. And yeah, once you're back, we will discuss some of the initial approach that I can think about this part 2, and then we will take it from there. So, see you in a bit. So if you're still here, let's talk about some hints. This is a very, very interesting problem. So if you read the question carefully, you will see that the base logic is still the same. So even in the part 1, the two things that we were doing initially, we will still have to do. We have to calculate the baseline path, or we can call it like a no cheat path. And there is exactly one path in the question that goes from your start to end. And while we are calculating the path, we need to maintain two kinds of scores. And this is very important in optimizing that. And it's basically derived from Dijkstra. And we don't need to use any heuristics or any fancy A star. You don't actually even need Dijkstra. All you need is very simple scorekeeping. So whenever you are traversing, you will maintain two scores. One would be from start and the other would be to end. And then there will be some X score, this will be some Y score, and this you will need to maintain for each tile on this baseline path that is there. And once you do that, this question does help us reduce the scope by allowing us to maintain unique cheats. So whenever you have a starting position of the cheat and ending position of the cheat, that is considered as a unique cheat. And this is very important, remember. So now, in your question, once you have this, in the second one, starting from the start position, you will have to do a simulation of up to 20 cheats, which means that you will have to look up to 19 neighbors with the end of the cheat always lying back on the path that was given to us. And the path is basically this baseline path. And what this will help us, this will give you back like different coordinates, and it can be up to 19 coordinates that I'm imagining, but it can give you like different neighbors where you can reach through the cheat. And basically we are considered about this path, right? And then we will get like bunch of coordinates. And what this will do is this will allow you to get back like a cheat start position, comma, cheat end position. And of course, for each tile as we are moving, we'll calculate the score. Basically, we have to increase the picosecond plus is equal to 1. But what benefit this will do is this will give us like some qualified cheats that we can run. And then what all we need to do is that we need to check that the pair of the cheat that we got does not already exist in the set that we are maintaining here for our unique cheats, which is also, remember, I told you that we have to maintain like a cheat start and a cheat end. And if it qualifies for both of them, and if it does not do that, then you need to just calculate the new, or let's make it simple. We have to calculate the cheat distance, which is basically your cheat distance from your cheat start to cheat end. Actually, you have to calculate three things. So let me write it again. I'm doing it more diligently because this is a little confusing. So ideally, what you need to calculate is you have your start position that was S. So you need to have a distance from your start position to your cheat start position. You will plus that, and then you will plus your cheat start position, comma, cheat end position. And then all you need to do is you need to do a plus for your cheat end position, comma, your end position. That was there. And in this one, whatever you get like this, let's call this a cheat distance. Once you get your cheat distance, or we call it short distance in short, all we need to qualify is this one, at least 100 picoseconds. So we need to check that if your baseline distance minus cheat distance, so this is minus, is greater than equal to 100, you will just say whatever your answer is equal to, answer plus is equal to 1. And then you need to maintain that. And this may sound like that this will be a lot of sample space. But remember, by having a unique set of cheats, it actually will make the calculation really fast. Because whenever you are looking for your cheats, just like the last part 1, it has to be somewhere on this base path. You cannot really start a cheat from anywhere other than this violet line that was there. So your cheat start position would be limited by one of the tiles on this position. And then of course you have up to 20 chances of finding a qualified neighbor. But again, by having a restriction that you have to come back to the path, and presumably you will have to come back on the path sometime after your cheat start position on the base path. Because let's say if I start a cheat from here, and if I go back here, that is not going to help me, because now again I will have to calculate and do the whole distance, and that will fail my calculation here. So I have a theory, by doing this and having enough optimization by storing the distance that we were maintaining here from start and to end, that will help our calculations by a lot, because that whenever you reach back to the path after doing a cheat, you don't have to do any further BFS. All you need to see is that on the tile on the path that where you have reached now, which is the cheat end, what is this value that is allowing you to do this? And you will always have this value before starting a cheat. So essentially all you need to do is you need to find like unique enough cheat starts in cheat end position, and that should give you your answer. And yeah, with this, I hope I was able to explain this, but this has been a revelation, right? Just by reading this, I think by writing really good code for our part 1, we here managed to make the part 2 a bit simpler to unfold and understand. And with that, I think I'm going to go ahead and write some code, and you should do the same. All the best. And hey, welcome back. And as you can see, we have received our second gold star for the part 2 of day 20. And surprisingly, this was one of the fastest part 2s for me, I think, in last few days. And I think all because we just spent considerable amount of time writing our part 1 and making it very extensible. So I was able to modify the same BFS formula to find the cheat. And I just put a variable where I could give the cheat length. So initially for the part 1, we gave the cheat length as 2. And for the part 2, we give the cheat length as 20. And yeah, using the set to find all the unique cheats and having this summation rule that I mentioned here, I was able to find the answer fairly quickly. Probably took like around 1.5 seconds. And considering I'm writing it in Python, which is not really known for its the most speedy performance, I consider that as a win for us. And this was one of those classic problems where I think the wording makes the question a lot more complex than it really is. And this is exactly how some of the lead code hard problems are. Like I have given interviews in Google, Microsoft, Meta, even Uber, and even Atlassian here. And usually if you're senior enough, I think L5 and above, in one of your coding rounds, there is usually a DP program with a memoization or like a lead code hard program, where actually the most of the complexity lies in your understanding of the language English, where you have to parse the language and try to see through all the sugar that is around the code logic. And once you're able to write it down in a simple words, and I think writing down is one of the most underrated skills that you can do. Once you're able to write things down, do some simulations, and try to visualize like what problem is doing and what problem really wants, like we did here, it does really makes it easy, because instead of then trying to waste your cognitive load in understanding the language and the puzzle, everything just goes away and all you have to then do is just follow the logic. And here in this question also, you can see there was a lot of fluff around programs, doing a race, having a race condition, doing a cheat. And essentially, if I take all of that away, the problem is fairly simple, that you have to find the distance from start to end, and you have a power where you can modify and consider some of the walls that don't exist. And now you can consider that as anything. You can call it a cheat, you can call it a superpower, you can call it a bonus where you can walk through walls because you're a ghost. You can just make a problem around that. But yeah, this was a really, really fun problem. And with that, we have completed our day 20. And I think we are inching closer towards the end. But yeah, if you enjoyed solving the problem, it would be really nice if you can like this video, share it with your friends, and subscribe to the channel. And yeah, with that, I'll probably see you on day 21. Take care. Bye.